Hi, I'm Ozan Unal, and I'll be presenting our work 2D feature distillation for weakly and semi-supervised 3D semantic segmentation. We begin by defining the task of 3D semantic segmentation, where given a 3D point cloud, the goal is to classify each point with a label. Due to the expensive and tedious nature of large-scale point cloud labeling, many recent works have switched focus to data-efficient settings such as weakly and semi-supervised 3D semantic segmentation. However, 3D segmentation models trained under such settings show weak performance on class boundaries, small objects, and distant regions. These errors are severely reduced when operating on a denser representation of a scene, such as with commonly paired camera images. With the aid of RGB color channels, 2D segmentation models are better able to separate class boundaries, and with the denser representation, are better able to detect and segment small objects and distant regions. Our goal in this work is to leverage this high-resolution image within our 3D pipeline to target these common weaknesses. Here, we will present IGNet, a 3D network that leverages image guidance while not only retaining the data-efficient setting, but also handling the mismatch between the horizontal field of views of the two sensors. IGNet is trained in 2 steps. We begin by training a 2D semantic segmentation model to generate per pixel high-level features that better capture shape and context for sparse regions. By training on synthetic data, we avoid introducing additional annotation costs. However, training on synthetic data yields yet another challenge. There exists a domain gap between synthetic images and real images that hinder performance in 2D. To further improve the quality of our image features, we propose using a domain adaptation pipeline to align our source domain onto the target. We further supervise the domain adaptation task via weak image labels, generated by projecting the LiDAR labels onto the corresponding image. Before moving on to the second step, we freeze our image guidance network. In the second step, as a baseline 3D network, we employ a mean teacher pipeline to also utilize the unlabeled points within our data. We establish point-to-pixel correspondence between the LiDAR point cloud and the camera image, and with an auxiliary head appended onto the 3D student, distill the information from the generated features onto the 3D network via an auxiliary KL divergence loss. With this auxiliary loss, the 3D network aims to mimic the more mature representation of the 2D network from step 1, for all points that have pixel correspondences. In other words, we introduce a new teacher model where boundary points along with small and distant objects are more richly defined as per the denser representation, to further and better guide the student on unlabeled points. As our image guidance module requires valid point pixel correspondences, the auxiliary supervision remains limited to points that fall onto the image. To extend the supervision to points outside of the image, we propose using a one-way contrastive loss guided by the teacher model, allowing points that fall within the image to guide points that fall outside. As illustrated, the loss extension aims to apply a pull force to all points towards pixels of the same category, while also applying a push to all points away from the pixels of a different class. We therefore align the features of points outside of the image with the features of the 2D image guidance network. Here we observe that the number of pixel to outside point pairings remains limited as each LiDAR scan has a fixed associated image. To combat this, we introduce a simple mixing strategy called FOV mix. We cut and paste an image with its corresponding points from one scene onto another. With FOV mix, we're not only able to generate new pixel point pairings to aid the contrastive learning, but also increase the variability within each mini-batch. Combining all proposed components, IGNet claims state-of-the-art results in both weakly and semi-supervised 3D semantic segmentation. Furthermore, we show ablation studies demonstrating the effectiveness of each component individually and the effectiveness of the image guidance in targeting the common weaknesses of 3D semantic segmentation models. To sum up, in this work, we tackle the common weaknesses of data-efficient LiDAR semantic segmentation models by leveraging rich and dense 2D image features to guide the training process. To generate such features, we use weakly supervised, domain-adaptive synthetic training to avoid introducing additional labeling requirements. Finally, we combat the horizontal field of view mismatch between the two sensors via contrastive training and data mixing to achieve state-of-the-art results on weakly and semi-supervised settings. Thanks for listening, and make sure to check out our paper.